Good morning and congratulations for finding the room. This is an IQ test. It's a very well hidden room. So as I pointed out in the first lecture, we'll have 2 extra lectures in the first week, but then you get some extra holidays because next week on Thursday I'm on a trip for a PhD, and at the last week of October I'm also not here, but for the rest, and then 2nd of November we lose, or we all have vacation, we gain back. So this way we are more or less on track. So this is the first extra lecture. There is another one on the 16th of October. We kind of agreed it would be 4 o'clock, but then I went to the administration and they said, no, 2 o'clock is better. We can see this in the student channel. As a professor, I never dare to contact my administration. If they say 2 o'clock is better, then it's 2 o'clock. Okay? I hope it's really better for you. I updated the schedule in Toledo, and I will repeat the warning that you don't show up at 4 o'clock. It's 2 o'clock on the 16th. Okay? So what we did last week is give the basic concepts of cryptography, explain how you can move confidentiality to confidentiality of keys, and we also explain how you can authenticate data either by hashing it to a short string and protecting the string, or by using a short key to then append like a MAC, a signature, to the message that the other party can recompute. So by sharing a short key, you can actually get secure communications. So you can make sure that nobody can read the communication and nobody can modify the communication. So this is a fantastic achievement. And so in modern cryptography, this is also now very cheap. So it's not expensive anymore. You can just add this to any channel, and the overhead will be very small. This means that all communication today is protected this way. For example, the Wi-Fi communication between your device and the access point, but also your Bluetooth communication. If you visit the website, it's protected like this. Bank transactions are protected like this. So more or less, a large part of communications are now encrypted. So also the web, I think we're now at around 80% of web traffic being encrypted. So there is now certain browsers that no longer allow an encrypted communication. So we made an enormous step forward in a very short time. There is still a problem we face, which is first we'll have to wrap this up, because so we ended with a MAC algorithm. Now in practice, you always want both. So I mentioned already that all communications are encrypted for confidentiality and then MAC'd for authentication. This is the standard. Although I must say, for performance reasons, to be very honest, until about 2000, people would just encrypt and hope that that was okay, which I explained to you last week. It's not okay, but people did it because it was too expensive otherwise. Or sometimes they only authenticated, but they wouldn't encrypt. But so then people started to try to find a solution. And really what we understood about 23 years ago, this is about 25 years after cryptography became an academic topic in 75. So after 25 years, we understood we really want something else called authenticated encryption. This is like an envelope where you put things in, and you can't see what's inside, and you can't modify this. So in modern cryptography, you combine those two in one operation, or in one application. So you don't have separate encryption anymore, or separate data authentication. Still, you will find legacy applications where this is not the case. And so this is something that started around 2000, but I think there is still work to be done to change everything to this setting. Now, one way to do it is very simple. This was studied about 20 years ago, which is you take an encryption primitive, you take a MAC algorithm, and you combine them. And now you have the question, how do you do it? You can, for example, first encrypt, and then MAC the ciphertext. We call this encrypt, then MAC. You can also do it the other way around. You would actually first MAC and then encrypt. So you first authenticate and then you encrypt. Or you could actually decide to do 2 operations separately. You MAC the plaintext and you encrypt the plaintext. But you don't MAC the ciphertext, or you don't encrypt the MAC, so you don't. So it's the other thing. Now, as you see, it's very interesting that actually IPsec, which is network layer security, and the most modern versions of TLS, so 1.2 and 1.3, is used for web traffic. They actually use encrypt and MAC. And today the consensus is this is the proper way of doing it. But it took quite some research and quite some study why it is. And it will bring us a bit too far to explain you why, but more or less the main message is you want to make sure the opponent can't change the ciphertext. And so you actually encrypt and then you MAC the ciphertext so nobody can change the ciphertext. You would detect it. But so 20 years ago, people were not so sure about this. So the old versions of TLS, they actually did MAC and encrypt. And the same thing for all the Wi-Fi versions. So if you see this, you know it's legacy, and actually there is some security problems. There may or may not be security problems depending on the specific details. It's all very delicate. But in general, today, we would no longer do this. And then around 2000, people said, this is really a bit ridiculous. So we have two building blocks, which we study separately. And then we tell people combine them properly. And if you mess it up, you can actually mess it up, which is bad. Also, in this approach, this composition approach, you still need two keys, one for the encryption and one for the MACing. So the question people ask is, can't we do this more efficiently with one key and just define one standard, one operation called authenticated encryption? And the answer is yes. So people have been looking at this, and since then this has been a very active topic. One of the things people worried about is associated data. And this sounds like very complicated. Why do we do this? Why do we want to make things so complex? We'll see this in the lecture network security. For example, if you have a network packet, it has a header and a payload. That's how networks always work. And the header says which protocol it is, what the source is, what the destination is, maybe give some more information. Now, obviously you want to encrypt this packet and you want to MAC it. But if you encrypt the whole packet, you just get a bunch of random bits. And if you send it to the network, nobody knows what to do with it because it's encrypted. So in fact, you can't do this. What you have to do is you have to encrypt the payload and authenticate the header plus the payload. It's even more tricky because, for example, IP has also a hop count, but every time a packet takes a hop, it's decremented. So you can't actually authenticate this because every node changes it. Right? So if you do this, so you have to be, it's a bit tricky and hairy, but more or less what you have is associated data, which you want to encrypt but not authenticate. And this is really what we need. This is called AEAD, authenticated encryption with associated data. That's really what you need. People want to be able to use parallelism. People want to start encrypting right away, so you don't want to have to wait until the whole packet is there, especially for long packets. People want that there is actually a proof that shows why the scheme is secure. And there is many things people keep discovering. So if you encrypt a packet and you authenticate it, it becomes longer. Now, many networks have a packet limit. So actually, by encrypting it, it may longer fit the limit. So now you have to fragment it. And so all these kind of things explain why it has taken us decades to actually get this all right and get this implemented. It sounds all very easy, but in practice, it's actually not so easy. So the last thing people are now worrying about is key committing. So they want to make sure that you cannot take a ciphertext and decrypt it with a different key and also get a valid plaintext. And why this is because, for example, there is a mechanism in social media where you can complain about harassment or about inappropriate content, but now your packet is encrypted, right? So you can send this packet to Facebook and say, look, this contains harassing content. But of course, if I, as an attacker, can make this packet decrypt in two ways with two different keys, then actually Facebook can't decide whether this was an innocent picture or not. So you actually want that you cannot create, for the same ciphertext, two different keys that decrypt the same packet in different things. It's called key commitment. Just to show you that there is still research ongoing. This is a problem discovered a few years ago, and so people still keep working on this problem. Just encrypting, it sounds very easy, but in practice, actually, it's very complex. And you have to deal with many things. And of course, people want it to be fast as well. What are people using today? Called Galois counter mode. We'll explain it in detail in a couple of lectures. Also CCM, used a bit less. This is CBC MAC counter mode. There is a more robust version of Galois counter mode called GCM Civ. There is also a faster version called OCB2. And this was already created in 2001, but it was patented. And so in fact, 2001, a lot of people made these kind of schemes. They filed patents. And then they started fighting and saying, your scheme is not secure. My patent covers your patent. And like, all these companies shouting at each other. And then the US government said, okay, we will and we will standardize something else then. It's a worse scheme than your patents, but we're not going to pay you. We're just going to standardize GCM and CCM. Well, OCB2 is actually a better scheme, but this is why you can't get rich in cryptography. Because if you make a cool scheme and you patent it, people will do something else. They rather use a slower scheme than pay you money. That's more or less why cryptographers mostly are poor. So at least we don't get rich with patents. So I designed a scheme together with one of my bright students called Aegis. This is also a very fast scheme. It's used by some large cloud providers now internally. It's based on AES. And the US government finished last year a lightweight competition, and they proposed ASCON as winner. So this is still, again, moving. People try to find better schemes, faster schemes. So the main feature of Aegis, it's 2 or 3 times faster than GCM. And for a cloud provider, that still matters. If you have peta and exabytes to encrypt, it actually matters whether the scheme is 2 or 3 times faster or not. Okay, so that was a quick wrap-up of symmetric crypto. Again, we'll come back to all those things in the next weeks, so it was a bit fast. That's okay. We'll revisit it in more detail. I'm going to spend a bit more time on it. So now we look at the problem that is actually great to have all this fast crypto, but how can you roll it out? If you want to buy something online, you have to send your credit card number, and maybe there is something you want to protect, or if you use social media, or if you use WhatsApp, we can protect this, but you first have to agree on a key. And how will we do this at large scale? Here in class, you could decide to generate keys and share them among each other. It would be quite, probably take a whole lecture before everybody has shared the key with everybody else. And then if you lose the keys, you have to start over and so on. So it would kind of work still on this scale, a few dozen people, but it doesn't work on the internet scale, right? You cannot say, hey, I want to buy something at Amazon or bol.com. And then Amazon says, okay, we'll send you a key. Give us your post address, and then they'll send you a key. And then after a week, the letter arrives. And then you type in the key, and now you have secure communication. This doesn't work in the modern world because we're all too impatient. If you want to order something, it has to arrive tomorrow. And we don't want the key even to arrive tomorrow. And then the packet the day after. So what symmetric crypto does, it moves protection of data to protection of keys. But actually, establishing those keys doesn't really work at very large scale. There is one very large system in the world. Well, there is actually 2 that actually have established keys with everybody. So all of you probably have at least 2 keys you've established with somebody else. Can you guess which ones these are? No idea. One is your SIM card. So your SIM card actually has a number and a key. And this is how the operator knows it's you, and they actually know who to bill if there is a problem. Okay, so in fact, the SIM card, what is in there essentially is a key. And there is also some cryptography in there, but yes. What? But that's not a key. That's not a key you share with the government. I will explain that later. So it's not the ID card, and also in fact, we are used to ID cards, but they're also popular in Estonia. But in most other countries, people don't have EID cards. So France is just rolling it out. The Netherlands is still discussing. When we started on the Belgian ID card in '98, the Dutch were discussing. They're still discussing, 25 years later. So it's not as massive as you may think. Yes, all Belgians have one, but it's not massive. The other one is your bank card. Actually, your bank card has a key which you share with your bank, and for every transaction is MAC'd, and the MAC is checked by the bank. So, but in both cases, it's a bit of a problem. And this is why the banks want to move to mobile banking, because they want to have a different way to give you this key. In the past, if you wanted a new bank card, you had to go to your bank and pick it up. And the same thing for your SIM card. You have to go to a telephone shop and pick it up and show your ID and whatever. And so, of course, they want to do this digitally, but this is large-scale systems with billions of users. Of course, every bank only has, or every operator only has millions or tens of millions, but still it's huge systems where there is somewhere in the bank or in this operator, there is a database with all the keys. And I can tell you one thing, especially for the phone operators, the intelligence services are trying to hack those keys. because they want to have all the keys of all the phones. Okay, and there is some very nice stories in the Snowden documents. So the French actually, they were producing those keys near Paris, and every Friday, knock on the door, the French state came, and they wanted all the keys of the week. Then at some moment, this was a bit annoying to send somebody there every Friday because of the traffic jams in Paris, so they actually made a digital connection. And guess what? The British hacked this connection, so they also got all the keys of this operator. So that's what's happening for this. There is an enormous battle for all these keys. So we really would like to not have this. Okay? So it's very risky and it's painful. So do we really need to do this? And the answer is no. So the answer was given by Diffie and Hellman, so two researchers in Stanford in 1975. So they actually found out that you can encrypt with a public key, and you can decrypt with a private key. So, of course, you need a different crypto system, but if you design it cleverly, you can make the key for encryption public, and you have a different key for decryption. It's a bit like your mailbox, right? I can put something in your mailbox, and only you have the key to get it out. So putting something in there, anybody can do. There is no secrets, or there is some parameter, but it's known. To get out, you need the key. Okay, and it's called public key cryptography, or also sometimes asymmetric cryptography, because the key for encryption and decryption is different. Has this solved the problem? No, because we never solve your problem. We moved the problem to how do you know what is Bob's public key? So public key encryption moves confidentiality of data to authenticity of public keys. Think of the mailbox. What I could do is write your name on my mailbox, and the mailman will come, put the letter in there, and now you can't have access, but I can. Right? So you really have to make sure that a public key belongs to a name. So you haven't completely solved it, but it's a lot easier. And we'll devote one lecture somewhere in November to actually how we link public keys to people. So this is another problem, and this is done, it's very easy on small scale. You know, in small scale, you can just each agree your public key, and that's it, and share it out. But if you have to do it by millions of people, you can't do it. Okay? And I can tell you the secret, we're going to shift the problem to another key. But that's only one key then, and then it stops. So Diffie and Hellman also realized that you could somehow do something else, and you could transform, it's not decrypting, but transform, we call this signing with a private key, and then anybody can verify with the public key. So this is a bit like a MAC algorithm. You take your plain text, there is no secrecy, but you take some key and the message, and you produce a short string of a few hundred or a few thousand bytes, and then you send this along, a bit like a signature on a piece of paper, and on the other side, you use the public key to verify that indeed this signature and the message belong together. So now you moved authenticity of many messages to authenticity of one public key. And so this is now I can comment on your point of the ID card. So in an ID card in Belgium, what is there is a public-private key pair to sign messages. And so you have the private key, but the government only has the public key. They don't have your private key. Okay? Whether the French state has the private key, I don't know, because the chips are French and German and whatever. But at least the chips are designed in such a way that the private key is generated in the chip and should never leave. Okay, so and this is how you can sign messages, or there's a separate key pair to log into government websites, and there is a third key pair to manage the card. But more or less, if you have an ID card in Belgium, you have a private key and a public key, and you can use this to sign contracts or sign documents or to log in. So for example, I now use my card several times a week to sign contracts. Finally, it has taken a long time. I mean, the rollout was 2004, so I think it's 15 years before I really started using it regularly. Actually, the pandemic made it actually, many companies switch to digital signatures. So we call this a digital signature. You can say, well, I don't use my ID card a lot. You still have been using signatures a lot for another mechanism that's very, very important for our daily lives, which is code updates. Every time you get a code update, and if you have a device, you'll get every week several updates, it actually is signed digitally by the developer. Or if it's an update for the operating system, it's signed by Microsoft or Apple or Google. So the first time you install Windows or you get your phone, it has the public key of, say, Google. It's in there. And the next time, Google signs this with their private key, and you can check that indeed this software update comes from Google. And so even if you hack the device, you only find the public key, you'll never find the secret key of Google. Okay? Unless you may have seen what happened a few weeks ago. So Microsoft lost some of their private signing keys to probably an attack by some large country in the East. So what happened, it's a very long story. It's also a big warning about security. So more or less, the keys were stored in the cloud, and then there was an error. So there was a core dump, which happens in case of errors, but Microsoft made a mistake. This core dump should have stayed in the production environment. But one person in Microsoft shipped the whole core dump to analyze it to a research or a development environment. And then they made some other mistakes. There was a whole string of stupid mistakes, but in the end, the signing keys of Microsoft were compromised. Which meant that for a while, somebody else could spread malware to millions or billions of devices officially signed by Microsoft, and all the devices would have accepted this. So this is, I think it's it's fantastic technology. We would not have good devices or this security level without all these signing updates. But again, in cryptography, you move all the problems to your keys, and if you then lose your keys, it's game over. Yes?
So we will never reverse the private key by the public key?
You cannot find the private key from the public key, no.
Even when the computational power...
Well, you assume that computational power is limited, because of course you can always try all possible private keys until you have the right one. But private keys are very long, thousands of bits, so you never succeed. Yeah, we already established last week that 128 bits is enough, but in public key the keys are much bigger. But there is very clever ways of doing it, and so you have to make sure your public key is secure. Okay? We'll come back to this. Now, Diffie and Hellman actually proposed these concepts in a very famous paper, New Directions in Cryptography, 1975, but they actually could not build a digital signature, or they could not build public key encryption. But they built something else called Diffie-Hellman key agreement, so they actually developed a protocol where Alice and Bob can agree on a secret key. So that's not the same as sending a message, hey, let's meet at 8 tonight. You can have a public conversation, and after the conversation you share a secret key, and of course then you can use an authenticated encryption mechanism to send a message, meet you tonight. But it's a weaker primitive because you can't choose the message, you can only agree on a common secret. And so how it works is very simple. I even hit some details, but there is somewhere a large prime, and large means 2,000 to 4,000 bits today. And that you don't have to search hard because they're specified in the standard. So the RFC say, use this prime, and it's a prime number of, say, 2,000 bits. And then you have a system parameter alpha, which is actually in practice 2. So you just have alpha 2. What Alice does is she generates a random number between 0 and p minus 1, where p is the prime, and she computes alpha to the x mod p. I hide the mod p here, but just to simplify things. But she takes 2 to the power a large number, and then she reduces it modulo p. So she takes the remainder by division of the prime, sends this to Bob. Bob does something similar. He generates a random y, computes alpha to the y mod p, and sends this to Alice. And now the magic happens. So Bob takes what he got from Alice, which is alpha to the x, and raises it to his y. And Alice does the opposite. She takes what she got from Bob, alpha to the y, and she raises to her x. And guess what now? You don't have to be a genius in mathematics to see that Alice and Bob have the same value, alpha to the xy mod p. Now the problem is that nobody knows, given alpha to the x and alpha to the y, how to compute alpha to the xy. You can multiply them, you get alpha to the x plus y. But nobody knows how to compute from alpha to the x and alpha to the y, alpha to the xy. Of course, one way to do it, if you could compute from alpha to the x, x. If you could do that, then you could do the same calculation as Alice. And this is a logarithm problem. So you say, hey, I take my calculator and I press log. Well, it doesn't work mod p. This is over the reals. But if you calculate modulo prime, we believe that discrete log is hard. If it was not hard, then you could actually find x. But as far as we know, it's hard. And if you find the way to do it, you can become very famous and very rich. Okay? Now, there may be ways to compute alpha to the xy without finding x and y. You can just compute alpha to the xy from alpha to the x and alpha to the y. Okay? And we believe this is hard. We call this the Diffie-Hellman, computational Diffie-Hellman problem. Okay? So we can't prove it's hard, but if you can't prove something is hard, then you make an assumption, which is that computing alpha to the xy from alpha to the x to alpha to the y is hard. This is known as the Diffie-Hellman assumption. So we believe Diffie-Hellman is secure because we believe the Diffie-Hellman assumption. And so far, nobody has found, so this is almost 50 years, has found a way to compute alpha to the xy from alpha to the x and alpha to the y. There is actually some positive results that you can show that for some prime numbers that solving computational Diffie-Hellman is the same as solving discrete log. So can we prove that discrete log is hard? No. We just assume that discrete log is hard. Okay? So, but magic has happened now because you have a public conversation and suddenly you agree on a key. It took a while to deploy Diffie-Hellman because later on slightly more efficient variants were found. But it was then shown, or people understood very quickly that Diffie-Hellman is actually more secure but more expensive. And then after the Snowden documents, people actually started realizing why Diffie-Hellman is so important. And so Diffie and Hellman, they won the Turing Award, which is a Nobel Prize in computer science, but only, I think, in 2012 or 13, so I had to wait a very long time. But today, you've been using Diffie-Hellman many times. Okay, if you use WhatsApp or Signal, that's Diffie-Hellman. If you use TLS, that's now Diffie-Hellman. So all protocols today use Diffie-Hellman. Well, not the Belgian ID card, but that doesn't encrypt. Okay, so with Diffie-Hellman, you can have an open conversation, and afterwards you share a key. And then this key can be used to send messages. But you can't actually send a message with Diffie-Hellman itself. So Diffie and Hellman were at the West Coast in Stanford. In fact, Diffie was first studying AI, but then he got bored with it, and he moved to cryptography. So he left MIT. But in fact, a few years after, a team in MIT called Rivest, Shamir, and Edelman, they actually found a way to construct public key encryption in digital signatures. And that's known as the RSA algorithm after the inventors, Rivest, Shamir, and Edelman. And I'll go very quickly, but it's also to do with number theory. So we have primes, but we start by choosing 2 primes, not 1 prime, and multiplying them together. Then we get the modulus n is p times q. And finding a large prime is not particularly hard. If you have good software for it, it takes a few hundred milliseconds to a few seconds. So it's not so hard to do this. Finding a good random prime is maybe a challenge, but at least you can find it. Then you compute some magic, and we'll study that later. This is a Carmichael function of p and q. You can choose an exponent e, which in fact in practice is always 3 or 2 to the 16 plus 1. For efficiency reasons, people want a small exponent. Cryptographers say use a large exponent, but this is widely ignored. At least we recommend to use 32 bits, but people use 3 bits or 2 bits or 16 bits. That's the most they want to do. And then you can compute a d from an e using this Carmichael number lambda n. Okay? So what you make public is this modulus n and e. So an e is very often 3, and then the modulus. What you keep secret is the factors of n or d. Now, if you have the factors of n, then you can compute lambda n, and also computing d from lambda n, it requires an inverse. This is, again, not too difficult to do, can be done efficiently. So more or less, if you have p and q, you can compute d from e. So how do you encrypt? You take a message m. This is the public part to the power e, which is also public. That's mod n, also public. And that's the ciphertext. So it's a bit like Diffie-Hellman. You use exponentiation, but in Diffie-Hellman, the base is fixed, it's 2, and the secret is your variable. Here, the base is your message, and the exponent is fixed. Okay, so it's a bit different, and also you don't compute mod p, but mod p times q. And then the magic of number theory happens. So to decrypt, if you raise c to the power d mod n, then you find the plain text back. And that's, of course, a bit of number theory magic, but it kind of works. So if you have the secret d, then you can take your ciphertext, raise to the power d mod n, and then encrypt. We'll go more in detail. I'll go a bit fast now. But so more or less, it's clear that if you can factor n, and n is public, if you go to my homepage, you'll find my PGP key there. This is for email encryption. It's 4,000 bits. So the modulus is public. There is 2 prime numbers of about 2,000 bits, but those, hopefully, you can't find. Okay? Because if you could find P and Q, then you could compute lambda n, and from lambda n and E, which is also public, you could compute D, and you could decrypt all my email. That's encrypted. But we believe you can't, so is factoring hard? Well, we don't know. We believe factoring is hard. Can we prove it? No, but mathematicians have been working on the problem for hundreds of years, and they've not made too much progress. I have here a simple example. So it's a 4-digit number. Anybody knows the factors? It's not so difficult to factor. 2419 is 50 squared minus 9 squared. So it's 50 minus 9 times 50 plus 9. So we factored it. So if you can write a number as a difference of two squares, you can factor it. The problem is nobody knows how to write a number as a difference of two squares. If you can do that, you can factor, but again, that seems to be a hard problem. How hard is this problem? Well, today we can factor something like 250 digits. So the record is about 800 bits. The Belgian ID card used 1,000 bits in the beginning. Now it uses 2,000 bits. And also the credit card system uses 2,048 bits these days. We believe that today the NSA can factor 1,000 bits, for sure. Because the factorization that was done with 800 bits was done a couple of years ago by academics. But then there is a very big concern because in the 80s, a Russian scientist, Yuri Manin and Feynman, the American scientists, they conceived the concept of quantum computers. This is now a big hype. Quantum computers, they don't have bits, they have qubits, and a qubit can be 0 and 1 at the same time. And if you can build a large computer, you have a very magical object because you can put there 10 bits, and they can be all zeros and all ones and everything in between. They, in fact, take 1024 values at the same time. And if you can put 20 qubits, they take 1,000,000 values at the same time. And if you take 30, it's 1 billion and so on. So you have enormous computing power. And these computers were conceived to actually predict physical processes. So people wanted to say it would be really cool to do all our physics calculations, to design new molecules, find new medicine by using these computers. And then in 1994, 30 years ago, Peter Shor actually showed that if you have such a computer, you can actually also factor numbers on it and compute discrete log. So the race is on. If you want to break the keys everybody's using today, RSA 2048, this is the number of bits, you would need about 4,000 qubits. But the qubits we can build today, so the record is a computer claimed by IBM, but they still haven't shown the details and shown that it works, is 420 bits. But they're very noisy, which means that you have to add quantum error correction, which is very, very complex. And so the current estimate is you need about 20 million qubits to actually be able to really calculate like 4,000 real qubits, ideal qubits. So it's going to take a long while. So the research on building these computers started in the 90s. They had a handful of qubits. And so then in 2001, 15 was factored on a quantum computer. It's 3 times 5. And then, so today, then they moved to the dozens. And today, we're like, the race is for hundreds. There is also an implication on symmetric key. The implication is not so big because I'm actually very skeptical that it really is a problem. And if you believe it is a problem, you just double your key length and then you're okay. This is why AES has a 256-bit version. Because then it would be really for sure immune to quantum computers. But I believe that even in 128-bit version, it's immune to quantum computers in practice. But okay. So it's very interesting that public key cryptography, the concept is 1975. In the first 10 years, it was just impossible to implement them. The computers were too slow to actually do RSA. It took a minute to do an RSA calculation, right? And then computers got faster and better hardware was available, so we pretend there was no market. Then the internet came, at least the World Wide Web and e-commerce, so then RSA became widely used. Then the Snowden documents came, Diffie-Hellman became widely used. In fact, now there is a new era, so Diffie-Hellman only had a period of a decade, Now the whole world is moving away from RSA and Diffie-Hellman to other new algorithms called post-quantum security. So we now build new algorithms secure against quantum computers. And the debate is on at this moment. So there was an open competition start 2016, but the research was happening much before. And so a month ago, the US government published the first draft standards, which is okay. So it takes indeed a long time to develop an algorithm. The algorithms are much more complex. I can't explain them on one slide. That's the bad news. So you will be much harder to understand, also much harder to implement. On the other hand, there is very ambitious plans. The industry wants to have migrated in 10 years to the post-quantum era. So they want to actually have all systems in the next 10 years use both RSA and these post-quantum algorithms. And then afterwards, maybe in 10 to 15 years, get rid of RSA and Diffie-Hellman forever. So this is all a very hot topic. So if you work in the security industry, I can be sure that for the rest of this decade, this will be one of the big concerns, how to migrate all our crypto. Because these new algorithms, they're a bit faster. That's the good news. But the keys are huge. So RSA key is 2,000 bits. All the other systems have keys of 5 to 10 kilobytes, signatures of kilobytes, or tens of kilobytes. So this is very, very challenging for many environments. So, but we always are busy. Okay, so public key crypto is great. So you can reduce protection information to authenticity of public keys. You can have an open conversation and agree on a key. So you can actually go to Amazon or bol.com, have an open conversation, and after the first interactions, there is a key between your browser and Amazon, and you have now a secure conversation. It's really amazing technology. And you can sign things. So a few of us sign documents like we did on paper. This was what people envisaged would happen. It still hasn't really happened. I'm still in a minority, I think, signing digital documents all the time. But we sign code updates now all the time. And also inside systems, if your machine boots up, this is very often also the startup code is signed, and the first thing a processor does is, or a system does, is checking the code, the bootloader code and the loading code, and the operating system is being signed so that you cannot compromise code. So we still use symmetric crypto because public key crypto is very slow. It's 100 to 1,000 times slower, so you can't use RSA and encrypt your hard disk with it, because then you would have to wait a couple of days. So you have, as I said, much longer keys. For RSA ECC, it's like 500 bytes, but for the new schemes, it's much bigger. Okay, so you see here, in the x-axis, this is the public key size. In the y-axis is ciphertext size. So what people use today, and I'll skip it, is elliptic curve cryptography. It's slightly more complex mathematics, but you have shorter keys. This is what people migrated to. And for example, Bluetooth is there. Some passports are there. I think also TLS is going in this direction. So RSA has larger keys and ciphertext. But if you look at all the candidates for post-quantum, so the smallest ones, so what they picked as draft standards are somewhere here, so several thousand bytes of ciphertext and public keys. And so there is some algorithms even still being considered. This is a coding-based algorithm where, as you can see, the public key is 0.5 megabyte. So this is going to be a challenge. Of course, computers are much bigger than 30 or 40 years ago, but still, for example, for contactless environments, where you just hold a card or a badge, and you have to send several thousand bytes of key and then do an operation and send the answer back, again, several thousand bytes, this is going to be challenging. And also many networks break. Right? Many networks work in short packages of a few hundred bytes, and suddenly you have to now send a ciphertext or a key encrypted, which is thousands of bytes. There will be a lot of work dealing with this, I can tell you. Nobody will be unemployed if you know how to deal with this stuff. So in practice, as I said, you use hybrid crypto. So this is a scenario where you have encrypt, then MAC. So we have two separate keys, just to show you the details. So you have a message you want to send, for example, a message in WhatsApp. It can be a photo or just a short text. What you do is you will first encrypt you generate a key for encryption and a key for macking. You will encrypt the photo and have the ciphertext. Then you will mack the photo and add the mack to it with the other key. And then you will take your two keys and you will encrypt those with the public key of the recipient. So the key is transferred using public key cryptography, because then you don't have to have a shared key. But the message, the picture of a megabyte, you will use symmetric cryptology. This is called also hybrid cryptology, but it's different hybrid. It's hybrids between public and symmetric cryptography. And so in the future, hybrid will mean old classical algorithms like RSA and post-quantum algorithms. So you have to be a bit careful with what hybrid means. How to decrypt? Well, it's very easy. You first start with the RSA packet. You decrypt that using your private key, and now you find the session keys. Then you can check the MAC. If the MAC is correct, then you decrypt. Otherwise, you stop and you don't continue. If the MAC is, and then if it's correct, you actually decrypt and you get your message. So this is known as hybrid symmetric asymmetric cryptography. And this is what's being used on the internet, for example, for all messages. If you use SSH or IPsec or TLS, you first agree on a key using RSA or Diffie-Hellman, and then, or in WhatsApp, the same thing, and then afterwards you use it to encrypt. Yes?
How do you divide K2 from the K1 plus K2?
How do you?
Divide K2, because MAC needs K2, right? But here your session key is only K1.
Oh, the session key is here, it's described here. It's a concatenation of K1 and K2. So these two lines means concatenation. You put them next to each other. Okay. That's a symbol cryptographers use all the time. We'll see it many more times. So these two lines, we use it for concatenation. So putting two things together. If you don't need secrecy, so like for code updates, many companies don't keep their code updates secret. You will not sign the full code, because again, if your code is 40 megabytes, like any app today, if you sign with RSA, it will take a long time. Plus the signature will be 40 megabytes. So there is a trick, and we saw the trick already. You first hash your code to a short string of 32 bytes, and then you will sign only the short string. This is called signature with appendix. So then what you send along is the short signed string, the signature, together with the code. What does the other party do before loading the code? You first hash the code to a short string. Then you take the public key and the signature, and you verify. If the verification says yes, you can run the code. If the verification says no, you cannot run the code. So why do we do this? Because it's much faster to only sign a short string. And so a hash function reduces a large file, like a big code update, to a very short file. That's, again, called hybrid cryptography, but combining symmetric and asymmetric. Okay, so quickly, and then we're going to come back to all these things in more detail. So I'll explain in the next lectures. We'll discuss symmetric cryptography, or even today we start already, hash and MAC. Then we have a lecture on signatures and public key encryption. Then we have a lecture on protocols. And so I'll give a quick overview of the next lectures as well. So one problem we have is, so I have now all these public keys. So at this moment, it's a big success. At this moment, there is 80 million web servers that allow for secure connection. And it's quite remarkable, because 10 years ago, it was something like 10 million. So we saw an enormous increase, and more or less all the web servers have now encryption. I guess the exception is some bakery somewhere or so that asked the grandson or to set up a website, and then the grandson moved on to other things, and this website still exists, has not been changed for 10 years. They may not have encryption and public keys, but in fact, the web is now fully encrypted. 80% is encrypted. Same thing for ID cards. If you want citizens to use government services, in the beginning, government used username password. This is really problematic, especially for health data or tax data. You just can't have this anymore, so you want better methods. And so the idea was to give every citizen a key pair, a public and private key. But also, if you work in a company, initially it was for email, but email never got really secured public key cryptography. This is kind of only for the geeks. But in a company, again, if you assign access rights, you give people key pairs, and then they actually get access using this key pair. So the question is, how do you link a name to a key? And it sounds very easy, but cryptography is mathematics, that's very easy. Dealing with the real world is very hard. The first thing is already, how do I define unique names? I said, that's easy, just take the first name and the last name. Yeah, well, how many John Smiths are there? How many Jan Peters are there in Belgium? Then you have Jan Peters 1, Jan Peters 2, Jan Peters, how do you find out which one is the one you need? Then some people have special characters in their names. Some people have Chinese characters in their name. So how do you deal with this? Okay, you can see this is actually quite difficult already in practice. So who decides on the names? Who is in charge of this? Is it the government? Is it Visa or MasterCard? Or is it a telco? Or who is the boss? This is a whole big problem. And then imagine that you establish a link between a key and a person, and this person is asked to leave the organization or retires, then you have to get rid of it. Or somebody is no longer a Belgian citizen, which is a bit rarer event. Or like Microsoft, your keys get stolen. Now you have to tell the whole world, this is no longer my public key. And this is much harder than linking a name to a key. It's actually get rid of the link. This is much, much harder. Because everybody in the world should know immediately that you no longer have this key. This is hard to do. And there is also the privacy problem. Of course, what you could do in theory is publish the name of all people with their public key, with their email address attached to it, but then you would, of course, have a big privacy issue. So the solution was conceived by a student of Ron Rivest, the R in RSA, in 1978. So Kohnfelder, he was called. And it's important to understand that in 1978, the world was offline. Okay, there were no online connections, so public key was designed for an offline world in which you had to check identities. So more or less what he invented was a digital ID card. If you take an ID card or a passport, a physical one, I don't know whether you ever looked at this. It has your photo, it has your name, it has your signature, so they can check if you sign somewhere else. It has a begin and end period, or at least an expiration date. It has a number. And also on the back of your ID card, it has the signature of the civil servant who gave you the card. And what does this card do? It says, well, this person is a citizen of Belgium, for example, and it links your photo to your name. That's what it does. So we have something similar in cryptography. What you want to do there is not link a photo to a name, but link a public key to a name. So more or less, you have the name, and this was designed in the 80s when the telcos were the boss, so they called it distinguished name. And so they had country, or you had common name, which is like your last name and your first name. O is organization, and C is the country. So this was very hard for you to imagine, but in the 80s we still had telco monopolies. So there was in every country one company in charge of all telecommunications. And if you wanted a phone line, you had to wait 3 months for this. 3 to 6 months in Belgium. Unless you knew a politician, then it could be halved. And if you knew 2 politicians, it could be divided by 4. But getting a phone in less than a week, that was impossible. And so it was a very bureaucratic organization, and they looked at the world by countries and then by companies. And so everything was very hierarchical and structured. But so what is there is actually your public key and your name and a serial number. And then with this symbol, what I mean, there is a signature. So in fact, we call this a certification authority, so a third party. And this party has one key pair, a private key and a public key. And with this private key, it will sign that this is your public key. It will link a name to a public key. Just like this civil servant links your photo to your ID, here by signing this, you link a name to a public key. And how do you check it? With the public key of the CA. So we now moved authenticity of public keys of 5 million Belgians to authenticity of one public key, namely the Belgian CA. Okay? And how do you protect that one? Well, you write it in every ID card, and it's available everywhere. It's very hard to find. It's very easy to find a copy and check it. Okay. So now what is the problem if you lose your card, or if there is a problem with your key? Like in the Microsoft incident, well, you actually want to produce a blacklist of revoked certificates. And for this, once a day, you publish a signed list of revoked certificates. It's called certificate revocation list. okay, or CRL. So more or less every day you say the following serial numbers are revoked. And in Belgium, this list is very long because if you get an ID card, by default, the keys are activated. And if as a user you say, I don't want to use this stuff, then your key pair is revoked. So in Belgium, we have every day, our CRL is 1 million items. It's quite long. It's not a big problem today. It was a big problem 15 years ago because it's like 10 megabyte over mobile connection. 15 years ago, it cost you a fortune. But so it's very privacy friendly because it just is a list of serial numbers. It doesn't give names, of course. It just says the following serial numbers are revoked. So if you want to check a signature, you should first check the signature on the document. Then you should ask for the certificate. You should check the signature on the certificate. Then you should download the CRL, the latest CRL, and you should check whether this certificate was not revoked. So you see it's quite a pain. And in practice, in fact, there is not one CA, but there is some CAs that sign other CAs, and they all have their own CRLs. So in practice, it's a big mess. Also, certificates are encoded in ASN1, and this is a nightmare to parse and to deal with. It's full of bugs, all the parsers. So this is where the hairy part of public key cryptography comes in. How does this work in your browser? Well, there is companies that issue certificates to Amazon, to Google, to whatever, to everybody who has a website. You have to pay for this, several $1,000s to get a certificate. And then you have a certificate, and then your browser shows a closed log. And so for them, it's a very good business model because, they just sign a message and they charge you $5,000. You just have to build a basement somewhere with a bunker, with some secure computers, and then a guard with a machine gun and dog around it, and that's it, right? And once you've made the investment of $2 million, you can now charge everybody $5,000 to sign certificates. So this seems like a very good business model. So in the 90s, there were hundreds of companies trying this. At this moment, there is still in your browser 600 CAs. Because all those CAs write their publicly in the browser. There is not one CA for the web. There is hundreds and hundreds, 600. And they all write your public key in your browser. And if you want a difficult task, try to find the list of CAs in all the browsers you have. It's in there. You can find it. And who is there? There is Torte. There is GoDaddy. This is the biggest one, VeriSign. In Belgium, we use GlobalSign. But also the Chinese government is there, the Turkish government, the French government, the Indian government. Why do I mention these governments? Because all these governments have been caught issuing fake certificates. So in fact, when they want to spoof their citizens, they actually make a fake certificate for Google, and then the citizen thinks, oh, now I'm talking to Google. In fact, they're talking to the government. Because in cryptography, we shift all secrets or all authenticity to this one party. If this party then cheats you. So what you should do is go to your browser and delete all the governments you don't like in the CA list. Right? It's a lot of work. And it's done to make it difficult. But so it does work, but it doesn't work. And so people were very upset about this. They made actually a service called Let's Encrypt. And so there you can get free certificates. There is no revocation. They just are only valid for 1 or 3 months. If you're hacked in the meantime, that's tough because there is no way to recall a certificate. But you also don't pay for it. And this is why we went from 10 million to 80 million certificates, because the next 70 million, they don't want to pay for this. Okay, so cryptography is used to authenticate yourself. So if you enter a password, which each of us does 1 million times per day, of course, unless you've been using the KU11 Authenticator, which is one of the startups of our team, where we want to get rid of passwords. But if you, for all the other sites, you still have passwords. So what happens is that the site doesn't have your password. So if you forget your password, they can't give it back. If they can give it back, it's a terrible site and you should not use it. Because what the site stores is the hash of a password. So they apply a one-way function to your password, together with even a parameter that's public we come back to this, to give everybody a different hash function, more or less. And so this is where cryptography is being used to protect passwords. So even if the site is hacked, you only find hash passwords. Of course, if your password is then easy to guess, you're still cooked. But if your password is hard to guess, you're kind of okay. So if you look at banking applications, there also, this is also what people in companies had. So I think until 10 years ago, something like this, if you worked for a company, the company gave you a small device to log in. And so this device showed a new password every 1 or 2 minutes. Today, this is an app on a smartphone. Today, Google and Microsoft have these authenticator apps. Of course, that means that they have the keys and they know everything. And of course, these devices were hardware secure. This is software security. But so now we have an app. But so this app has a secret key. And so more or less what happens is that the server has a secret key too. It sends you a random question, which you have to type in. Or if your smartphone is connected, it goes over the connection. And then what your device computes is a MAC on this string, and this is being checked. This is like signing it. And this way, it knows it's you. And every time there is a different question, so you cannot take the answer from yesterday or an hour ago. There is every minute, there is a new, or every time you try to log in, there is a new question. That's called one-time passwords. They're not very secure because in some websites, it's only 6 digits. Because people are lazy, they don't want to type more. So which means you can now write a simple script and run to all the possibilities, and eventually you'll get in. And you can say, oh, you can detect this. What you then do is you try the same code for all users. Because you can't detect attempts for users, so you can say, okay, this guy tried to log in 100 times, you now block the account. But if you do the same attack, but you change a user every time, then you can keep trying 1,000,000 times and you will be in 1,000,000 times. And if your script is fast, you will be in a few seconds. So it's not very secure, and luckily the K11 authenticator doesn't use symmetric crypto, it uses public key crypto, where the same thing kind of happens, but it's a more complex scheme, but this is what, for example, is used in the credit cards. So the terminal has your public key, gets it from a certificate, it sends you a random number, and the card will sign this. And so again, this proves it's the card. The nice thing is now there is no secrets in the terminal. So in this case, the previous setting, there is a secret key in the server, and there was a company called Secure ID. They actually were producing these devices. Then they bought the RSA company because they made much more money with these plastic devices with crypto from the 80s than with the very fancy RSA algorithm. So they bought RSA. They called themselves RSA. Guess what happened? They were hacked. And so the secret key was leaked. And so millions of employees, also of defense companies, government employees, had to get a new device. Right? So that's the problem of this approach as well. That once you're hacked, all your keys are lost, and you have to give everybody a new device. So this is why you want public keys. The problem, of course, is if you sign something, this is not 6 digits. Unfortunately, an RSA signature today is 2,000 bits, so that's 660 digits. You cannot ask somebody to type this. They will go nuts if you do this to your users. Okay, so then it means it only works if you have a connection. And if your device is connected, it can send the signature. Or, for example, the credit card, your Visa or MasterCard, you have to put it in the terminal, and then it gets a request and it signs it. Okay, so this is how you authenticate, and it's also how you use the ID card in Belgium. If you log into a website with health information or tax information, you can actually you get a random number and you sign it with your ID card. So it's not the same key used to sign a document, which is a separate key. Here is a challenge is being signed to prove it's you. Of course, there is also It's Me. Have you heard of It's Me? Well, It's Me goes back to this model. It first uses your card once, and then it stores a secret key somewhere to go back to the 80s. But only the first operation needs your ID card. So cryptography is now used to protect your hard disk. So, in fact, today, you can install software to encrypt your hard disk. With BitLocker is from Microsoft, and you know for sure that Microsoft keeps a backup of the key for you, that the NSA has access if they need to. It's very convenient. And there is also open source software where you are in charge of the key. Of course, if you lose your key, you lose all your data. But if you go to a store like Fnac and you buy, or bol.com, and you buy a hard disk, it actually will have AES built in, and everything will be encrypted on the hard disk. Amazing. But if you take the hard disk out of your device and plug it in a different device, it will still work. Because for normal users, there is no key management. So there is no authentication or key management, which means that there is encryption but no security. So it's not because your hard disk is encrypted you have security. Right? If your hard disk is really encrypted security, it means that if you take the disk and plug it in a different device, it doesn't work until somebody enters the key. Which also means if you forget the key, whatever happens, you will not get your data back. And so this is why the industry doesn't want to give this to people, because then they will forget their key and then they will shout at them. Okay, so you just put the encryption, but you make sure it always decrypts, and the key is just stored next to the hard disk, so you can always decrypt if needed. Encrypt databases, file encryption. There is also data in the cloud is being encrypted. So the big question is not, is it easy to encrypt? Yes, it's easy to encrypt and decrypt. The question is, how do you manage the key? And if you lose the key, you lose the data. So if you work for a company and you work 6 months on a project, and then something happens to you, or you leave the company and they don't have a key, then they lose all your work. This is why companies want a copy of the decryption key, because, and also you want it, because if you forget it or you store it somewhere and it gets lost, then you have a problem. So the second main application is network security. There is a lot of protocols, and more or less there was a big debate, what should we secure, at which level should we secure, and the answer is now at all levels because it's so cheap. So if you can use IPsec, it's still not common, but you can do it. For example, in VPNs, it's being done. You encrypt the network layer. What you don't see here, because it's not part of the internet standards, you also encrypt everything at data link layer, so from your device to the access point for Bluetooth or for Wi-Fi or for 2G, 3G, 4G, 5G. You encrypt the wireless part till the network, and then it's decrypted. But so you can also encrypt at the VPN layer. So VPN, IPsec layer, you can encrypt at the transport layer. This is TLS. This is what's being done for web traffic, but also for downloading email and so on. So TLS is widely used. And then you can also encrypt in Signal and WhatsApp and so on. So in fact, if you send a message over your mobile phone here over to Signal or WhatsApp, it's encrypted at least 3 times. Or at least 2 times, but probably 3 times. So once by WhatsApp, if you use a VPN, or which you should do if you're in a public place, then it's by the VPN, which can be TLS or IPsec based, and then the Wi-Fi encryption comes on top. And this is kind of unbelievable, because in the 90s we were all arguing, where should we put encryption? And the answer is now everywhere, because it doesn't cost anything. So as I said, data link layer, this is very convenient because it's transparent for most users. It can be used for wireless LAN to limit access, or 2 or 3G or 4G. If you don't pay, you don't get the key and you can't send, right? Or you can't talk. But it's not very secure, because anybody who has access to the access point can read everything. Right? Even in an internet cafe, if they use a secure encryption, the owner of the internet cafe sees all the clear text. Right? Even if you use the most secure Wi-Fi settings, Wi-Fi is only till the access point. The most studied protocol is TLS, and I really like this slide done by Doug Stabela. I should get an update of it. So it shows you many things, namely that network security is complex. So today we talked a bit about the crypto algorithms, but then there is also details like how you derive keys and MAC and encrypt, or encrypt and MAC, and all kind of these painful things. Then there is alerts. If something goes wrong, you've used the key too much, or maybe you closed your browser, you reopen it, should we now make a new key, or can we use the old key? All these kind of technical details, very often driven by performance. Then you implement this using a library, and there is again dozens of those, and then you use it in an application. So this slide shows you all the attacks on TLS. Okay? So the main message you would have from this is that TLS is not secure. It's just the opposite. TLS is the most studied protocol, and at least TLS 1.3 is resistant against all these attacks, as we know. Okay? And even for the lower parts, there is mathematical security proofs. For some of the higher parts, there is now formal methods. So, for example, there is a team in France that has taken the TLS 1.3 spec and produced code which you can prove formally that it's the same as the specs. Okay, which is quite an achievement. And the code is quite fast. It's not as fast as the handwritten code, but it's still 30% slower. But for example, Mozilla uses it. So in fact, there is enormous progress, but this has been the most studied protocol. So it was designed in first version 94, last version 2018, TLS 1.3, but is the most studied. So the main message is that if you use a different protocol or your own protocol, you haven't seen all those attacks. And they probably still also apply, but you don't know yet. And of course, the other message is that it's too complex. So if you make things so complex, you will have many problems. So keep it simple. And the other thing is, if you want to get attention, you should give your protocol a cool name. So we made a very big mistake. We called our attack the cross-protocol Diffie-Hellman easy DSA attack. Nobody cares about this attack. If you call your attack beast or crime, then you make it to the press. But if you call it cross-protocol easy, it's a big, big mistake. You have to find first a cool name for the attack and then explain what it is. Okay? So in a VPN, you probably heard the term before, there is several models. It's also a very complex world. You have host-to-host, so more or less where you make a secure tunnel no matter what happens between two machines. Okay. For example, this is how I work from home with the machine in my office. And so there is a secure connection and nobody can log in. Now, another approach used, for example, is K11 has 7 remote sites or 8 remote sites. So to connect those, you put a gateway in every site, and they talk to each other securely. So they use a public internet or open connections. But all the K11 traffic, say between Leuven and Kortrijk, is encrypted. So if you intercept this, you don't see anything. Okay? And then if you work at home, what K11 wants you to do is actually to take your laptop and log into the K11 gateway. Okay? And there you have a secure connection from your device to the gateway. This is how most companies work. And then after the gateway, everything is decrypted. So why do companies not like the top solution? I use this solution, and I can tell you I'm very much hated by the ICTS people for this. Why do companies hate this? Because they can't look inside. They want to see what you're doing. They want to block your Facebook traffic. They want to detect what you're doing. They want to find out whether you download viruses and so on. So companies like this approach because they want to see what you're doing the whole time, right? So if you do it like this, the company has no visibility on what you're doing, and so they say you're a security risk for us because you bring an outside network inside and we can't see what's happening. So you see that actually security, your security and your company's security may not be the same. And so in security, you can have very interesting discussions. Who is right? I don't know, but yes. Well, that's a very good question. Let me first say I'm not a lawyer, but in Europe, it's not allowed for companies to look at your personal communications. Of course, if a letter arrives, say clearly having invoices so they can look at it, but it's remembered that you actually don't do private stuff at work, but in Belgium, companies can't look in this. I mean, I can give an example. A long time ago, we detected a hacker who was trying to actually crack our passwords. This is now 90s, and this person had set up an account with a mailbox, and we had looked in the mailbox to see what he was doing because he was mailing stuff to himself to another account, and then the lawyers told us, you can't look at his mailbox, this is private. So even hackers have privacy in Belgium. If something is mail, it has the same protection as letters, and you need an order of a judge to look at it. Okay, so in general, in Belgium, you have a decent protection. Okay, having said that, so indeed, if you use TLS channels, you can actually TLS to Facebook. They can still block the Facebook website and see that you go to Facebook or Meta, where you can block the address. Plus, there is companies that sell special servers that actually issue fake certificates for all the servers. So they can call meet in the middle service. And Europe loves this. So after TLS was produced, Europe made a version called ETLS, Enterprise TLS, which is easier to backdoor, for which is easier to actually put such a server and interrupt all TLS connections by the company. And the banks insisted that they needed this to be compliant with regulation, because they said we have to inspect that our traders don't exchange inside information, and so we have to interrupt all TLS connections going out of our trading room. And so they wanted it to be a standard, which is another question. Should we really standardize something like this? I'm not sure, but okay. So is this legal? It depends, right? At least, yes, you still have more privacy. If you work in the US for a US company, yes, the answer is it's legal. In the US, you have no rights in that respect to your company. In Europe, it's not so clear, but it's not so clear what a company can and cannot ask from you, but technically it's feasible. And it's a failure of cryptography. But not the cryptography, it's actually the key management that's being attacked. So it's really amazing that, running a bit late, but okay, let's finish this and then give you a break. So when I started in cryptography, it was in the 80s, there were probably less than 100,000 cryptographic devices in the world. There were the first bank cards coming, ATM machines, but then the bank cards only had the key, they had no cryptography. The cryptography was a little bit in the bank machine, but there were probably less than a few 100,000 in the world. Today there is something like 90 billion cryptographic devices, but most of these devices are there to protect the industry against you. So we don't protect Alice and Bob, we protect the government and the companies against the users. It's like your bank card. People think the bank card is there to protect their money. No, the bank card is there to make sure you don't spend more money than you have. It's a little spy you have in your pocket that allows you to spend exactly as much as you have and not more. Okay? The same thing with these badges of K11. They're not there to protect you, they're actually there to protect K11 property. To make sure you can only get in when K11 wants it, and they have a log and they know where you've been all the time. As far as I know, it's not being abused and it's being carefully guarded, but in principle, they know exactly which building you enter. In my building, they can even detect who goes to the toilet how many times if they want to, because you have to badge to go to the toilet or to come back. So it's really, they don't do it as far as I know, and you probably would have a privacy problem, but the technology allows it and can actually, it's not to protect me, this technology, right? It's to protect the organization. Same thing in your smartphone. The smartphone has all this cryptography for updates. But imagine there is an update and you don't like it, or you only like half of it. What can you do? Reject it, yes, but then you have probably security problems. But you cannot say, I like those 3 features, but I don't like those 2. So in fact, you're not in control. It's the company decides for you what will come. It's a way to have control over your device. I will not even speak about DVD and Blu-ray. These are all technologies, but Netflix is the same thing, right? Netflix, they see you as the enemy because you want to share your password with other users, or you want to share the videos you paid for with your friends. So for Netflix, you're the enemy. Netflix cryptography is there to make sure you can't do what you want to do, and that you can only do what you pay for. So cryptography is not used to protect Alice and Bob. Alice and Bob are the criminals for Netflix. Also called customers, but for the cryptographers of Netflix, you're the bad guy. Okay? So there is some cryptography to protect us, like in our phones. There is encryption, but it stops at the base station or base station controller. And this is deliberate choice. It's not that we can't do it further. It's because the government wants to eavesdrop on all communications. And even in 5G, you know, I like to go to these meetings for these people and say, and what about 5G end-to-end encryption? And then all the people from the telcos like to look at the ceiling and the floor and they don't say anything, right? So in some sense, we're going to build our whole society on 5G, all the factories, all the cars, everything will use 5G and 6G, but no end-to-end encryption because then we can't listen in. We have the web, but it's very secure unless you can produce fake certificates. That's why I call it wet. Then I think the most secure devices we have actually are our phones. So in fact, your data on the phones is probably, of course, if you make backups, it goes to Google and Apple, hopefully encrypted. But that's probably the only device where we really have good protection, where it's really hard for government and others to get access to. But of course, Europe now wants to change this with this chat control regulation. They want to be able to scan in real time all your content on your phone in case there would be child pornography on there. So this is the big debate now happening in Brussels. So the only thing which I think is green, where we really have good protection in billions of devices, the government wants to get access to. We have all this messaging. You still use WhatsApp? Anybody uses WhatsApp here? You should use Signal, because WhatsApp encrypts your stuff, but all the metadata, which means who you talk to, what are your contacts, what do you send to whom, this is all being collected. And so WhatsApp is okay, but your metadata is actually collected. Plus, WhatsApp has this fantastic backup feature. So what happens if you drop your phone in the toilet? It's dead. You go to the shop and you buy a new phone. And then you log in and all your messages are back. Where were they if they can come back? Because they're now in the toilet in a broken device, so they must have been somewhere in the cloud. Okay? You have only two options. The option is to switch off this backup, and then it means, like in Signal, if you have a new phone, everything is gone. You have to start over. But if you want to get everything back, which many people click on, then in fact it means that there is a copy of all the messages in the cloud. So this is why you should use Signal and not WhatsApp. Skype is also a very good example, probably too old-fashioned for you, but it was really a breakthrough, because maybe it's hard for you to imagine, but I had a phone bill of hundreds of euros, mobile phone bill, just traveling in Europe. Hundreds of euros, just for even short calls of 5 to 10 minutes, cost a fortune. And so when Skype came, they actually managed to use internet telephony, bypassing all the firewalls, and you could actually call for free or for a very small amount. And Skype was distributed, so there was no central server. And Skype reached a few hundred million users. So what happened to Skype? It was bought by Microsoft for 13 billion, and within 1 month, the NSA had access to all conversations. So you can read this in the Snowden documents. I'm not making this up. So it's clear that as cryptographers, we try to build secure systems, but part of society doesn't want us to have this. Okay, so finally, if you take the more advanced crypto course, you'll find out that we're doing something else. So in principle, we can protect stored data, we can protect communicated data, but where now the new battle is protecting data during processing. So we kind of have understood that all our data is in the hands of other players. You can't get today any medical treatment without the hospital taking pictures of you and photos and storing a lot of measurement data on you. You can't use social service, social media to use your data. Everybody uses data. So there is now a big battle happening. And so the industry wants to sell you computing and encrypted data. Or it's the cryptographers, but the industry wants to sell you trusted execution environments. So the industry understood that, like, yeah, well, no, things are not secure, but maybe you're very important, you're a bank, or you have health data. What we're going to do is we're going to put a secure processor inside our processors, called SGX or SEV, so Intel SGX, ARM SEV, or, sorry, not ARM SEV, AMD SEV, ARM has Trust Zone. This is on your mobile phone. And say, trust us, you have your really important data, we'll put somewhere inside the computer, in a secure computer, and nobody will have access. Okay? Nobody? How do you know that the NSA doesn't have access to it? So, but that's where the industry is going. So cryptographers, we have something better called computing on encrypted data. They say, instead of trusting the US government, why don't you trust cryptographers? So there is some very fancy techniques, like you can encrypt and compute on ciphertext, or you can put your data over multiple servers. And there is lots of fancy mathematics, and this was conceived in the 70s and 80s, and it's practical today. So today there is quite some startups in this space. Practical means still 100 to 1,000 times slower than normal processing, but it used to be million times to billion times. So in MPC, what you do is you split your data in shares in such a way that each share gives no information. So it's not that you have half the photo or so, you just get random data, and then they all compute on this data, and at the end, the result comes out. And unless you compromise all but one servers or the majority of the servers, you don't have any view on the information. For example, this is now how some cryptocurrencies store their secret keys and do the transaction processing. It's also used for the US Census. It's also used by Facebook to compute information on users together with vendors. So Facebook has a lot of data about you. Companies selling stuff have a lot of data about their customers, but they don't want to share this data because they're competitors in some sense for the same users. So they use MPC to compute information about customers without sharing private data. It works quite well, but the communication overhead is horrendous. So you have to send gigabytes and terabytes of data. So the other technique requires much less communication. You just encrypt everything to shoot ciphertexts, and then you compute on the ciphertext, and the result comes out and can be decrypted. This sounds like magic, but it can be done. It has much less communication, but it's very, very slow, so it can only be done for simple functions. But for example, where the state of the art is today, you can take a neural network with 50 or 60 layers, and you can compute it completely in an encrypted domain. And of course, if you do this in clear, it takes milliseconds. If you do this in an encrypted domain, it takes seconds. But for many applications, this is good enough. And for example, Intel and other players are now building special hardware to support this to make it even faster. So this is where the future is. And of course, with this, we can do cool stuff like voting, security for cryptocurrencies, privacy-preserving tracing, analysis of data, so big data but privacy-friendly. So there is lots of applications. So in general, what I showed you was applications where you have a cloud server, but of course you can also have applications like contact tracing where everything happens inside the phone. Why should you send all the data to a central server? This phone has more computational power than a Cray from the 80s. It has more storage than a supercomputer from the 80s. Yet what we all do is we set it up that all the data goes to a central place that decides for us and then gives us the answer back. Why can't your phone compute a route when it's offline? Really? Is it so difficult to compute a route on a map? Do you believe that? That you can't, this device can't do that? It has like 16 processors, whatever. It has gigabytes of memory. Why can't it compute a simple trace on a map? Right? So I think it's, of course, a business model, but we can actually build devices where everything stays local. Good, so time for a break. Sorry for a bit longer, so we'll have a shorter session after the break. So there is an article not summarizing everything I did. Oh, sorry, I think we should skip the break and I'll just do a few more. Is that okay for you guys? And we'll end a bit earlier. I hadn't seen it was so bad. Sorry for that. I got too carried away. But it's such a fascinating topic, right? So there is a short article on Toledo that's where you can read the basic principles. It doesn't have everything about the second part, but now you have a good overview of the whole course. Okay? And so now we dive into the details of symmetric cryptography. That's what we'll still do for the next 10 minutes or so. And I can hand out the slides already, then you have them already. That's already something achieved. So you can pass this on maybe. Good, so we'll say a few things about stream ciphers and block ciphers. Choose parameters, explain a bit how it works, and how to use block ciphers will be for next week, of course. So it's symmetric crypto, so Alice and Bob share a secret key. There is a few more if there is missing. So stream ciphers is like what you have in your mobile phone, A51 and Snow 3G and RC4 you used to have in your browser. Luckily, it's gone. Block ciphers, I mentioned DES already, and AES, and then how to use block ciphers securely. So block ciphers are more common because they're more like the Swiss Army knife. You can use them for many other things. And also because the US government decided to standardize block ciphers and not stream ciphers. So stream ciphers I mean, the death standard was done in 1977, and so everybody knew what the standard block cipher was, recommended by US government with a too-short key, but okay, it had a stamp of approval. While stream ciphers in the 80s was still the area of all kind of secret designs and many weaknesses and governments backdooring things. I mean, it was very interesting times. So I was working for some financial institutions trying to figure out which stream ciphers, how they looked like and whether they were really secure or not. So it was a very obscure world. And it's still not widely used, although stream ciphers have an advantage that actually, per computation, they can give you more efficient encryption. So they're slightly less flexible, but if you really need stream ciphers, they're actually faster for the same energy consumption, for the same number of gates, for the same number of cycles. There's a long history. I will not go into the history. Unfortunately, I don't have time, but just to show you that stream ciphers have a long history. And initially, all these mechanical devices like Enigma were stream ciphers because people encrypted things character by character. And block ciphers in the beginning, DES was there in 77, and then people didn't do very much until AES. Now, of course, there is also hundreds of block ciphers, but that doesn't really make sense. What you see also is that we now see some widely designed stream ciphers being standardized, mostly in the mobile sector, SNO 3G, Zook, and SNO 5, so SNO 5G. So you have it in your phone because it's more efficient. It's used in phones. And also Google uses ChaCha20 for TLS. Although the rest of the world doesn't quite agree with Google. But so stream ciphers are a finite state machine. They typically operate on small quantities, so bits or bytes. It used to be characters from A to Z, but now it's bits or bytes. Some of the most modern ones work on 32 or even 64-bit words, but historically you were actually dealing with smaller things. And we also look only on synchronous stream ciphers. There were also stream ciphers that could kind of hook up to a connection and synchronize automatically, but this is completely gone. It's a historic fact. So we showed this slide already. So it's what's inside there looks very complex. It's very simple. It's a finite state machine. You have a state, and every clock cycle you update the state and you produce some output. And then how do you initialize this? Well, you take the key and the IV and you initialize the state. The key may also influence the next state function or may influence the output function. In fact, the key can influence any of those three, but at least one, of course. If you don't use the key, then it's not secure. But in most designs, the key only influences one of the things. Sometimes it's the initial function, initial state. Sometimes it's the next state function. Sometimes it's the output function. It depends a bit on the stream cipher. You can argue it's better to do the next state function, but that would bring us too far. So more or less the goal is to build a small efficient machine. In the beginning it was with rotors, mechanical, then electromechanical, and now with logical bits and bit operations and word operations. But you want to put in the device a short key and an IV and get out a random stream. And for every IV you should get a different random stream. And so then you use this to encrypt. So it's a bit like the one-time pad, but now with a short key. That's the main thing. So the question is, how can I build an efficient and compact machine that produces random bits? So before we go into the details, so it's called synchronous stream cipher because the recipient has to be synchronized. They have to know where you are in the sequence, right? If you lose a few bits, which some initial communication systems, some standards once in a while lost bits, then you have a big problem here. Because if there is a bit gone, then the decryption will not work anymore. Okay, so you assume that sender and receiver are synchronous. That's why it's called synchronous stream ciphers. So the reason why we see stream ciphers a lot is because we have more and more wireless communications. And in wireless, you always have errors. So that can be just a small disturbance, a double signal. You can be on your bicycle and you pass a tree, or that can be a temporary switch, glitch on the network or something like this, but you have errors. And so in a stream cipher, if you have one error in your ciphertext, you also get one error in your plaintext. But in a block cipher, as we will see, it's different. There, if you encrypt AES, if you encrypt 128 bits at a time, then one bit error in the ciphertext will generate 128 bit errors in the plaintext. So this means that AES as a block cipher cannot be used as is in wireless. We will show you how it can be used anyway, but at least not by encrypting block by block, because that would mean that your conversations would become unintelligible, and if you browse on the web, you would get a lot of weird pictures and whatever. It just doesn't work. So for communications, what really matters is error propagation. So this, at data link level, you always have to use ablative synchronous stream ciphers. The nice thing is that this machine, the disadvantage is it has to produce an output every clock cycle, okay, or at least every phase, every state of the machine. But you can compute it in advance because it doesn't depend on the plain text. So if your plain text is sometimes fast and sometimes slow, in fact, you can build a constant time machine and make a buffer, which is very nice. And also, as an opponent, I can choose how the machine starts by maybe controlling the IV, by making a specific packet IV, but I can't influence the machine while it's operating. So the machine is started and now it runs. And I can only look at the output, I can no longer change it. Right? In a block cipher, you give it inputs and inputs and inputs. You can influence how it works. Here, you start it up, and then you can no longer control it. Which means it's a bit easier to make a stream cipher in the sense that you have to think of less attacks. So you can take more risks, which is what people do. So I already mentioned the transmission in depth problem. This is explained in detail. So I think I can go now a bit faster. So you have to make sure that a key stream is never reused. This is the Venona problem, remember? If you have twice the same key stream, then you can XOR the ciphertext, and then the keys fall out, and then you get the XOR of plain text. So to make sure this doesn't happen, you have to make sure that every message or every packet has a different IV. And you have to absolutely positively make sure that the IV does not repeat. Otherwise, you have a big problem. And if something happens to your device, there is an alarm state or a reset, then you can't put the IV to 0 and start over. You also have to agree on a new key. So this is essential. You have to make sure the IV never repeats. And that sounds easy, but in practice, it's not so easy because devices can break down, can crash. Maybe if you look at the cloud environment, there you make in cloud environment, the environment manages everything for you. So if a process crashes, the cloud starts up a new one for you. You have to make sure that this process uses a different key because it will not remember what IV the other one used. So you have to think of it very carefully. In that sense, using a stream cipher, you have to be careful about not reusing things. So why people use it? Because in software, it can be 5 times faster than AES. Of course, unless Intel and AMD cheat and they add an AES instruction, then you can, of course, no longer beat them, right? If they put hardware instructions for software, then, of course, the hardware will be faster. This is why on most processors, AES is faster than all stream ciphers, because there is hardware support for it. But if they would add hardware support for stream ciphers, they would win again. But this is also why, in, for example, your mobile phone, where encryption is done in hardware, so the encryption of your voice or data connection is done in hardware in the phone, and this is done using a stream cipher, because it's cheaper. Okay, so in hardware, you can do it with less gates, or you can get better throughput per area. So if you look at the metrics, this is why we have Snow or A51, where mobile devices actually don't use block ciphers as much. And so in wireless devices, in medical communication, you still see stream ciphers as well. So from the 60s, 70s onwards, people started to build stream ciphers based on linear feedback shift registers, a very nice object, very simple. So every square box here is just a bit, a 0 or a 1. If you're a hardware engineer, it's a D flip-flop, so you can store a 0 or a 1. And it's called a shift register because every clock you shift everything left. Now, of course, then you have a free position on the right here. What do you put in here? Well, you put the sum of the 4 blue bits here. Okay, so you first take the sum, then you shift everything left, and then you put that one here. That's how it works. And so this is how you advance this. If you look at this, what comes out actually is amazingly random. So if you look at the sequences, like you can see how many zeros and ones, and how many times 0, 1, and 1, 0, and 0, 0, and 1, 1 is actually very nicely distributed, so it looks very random. So these kind of circuits are put in chips to test them with random inputs. So this is why it's being used. If your register has L positions, it will repeat only after 2 to the L minus 1 steps. Why not 2 to the L? Well, if you design it properly. Why not 2 to the L? Because if you initialize as 0, it will stay in 0 all the time. So there is one cycle 0, 0, 0, and the other ones, if you design it well, you can run to all the other steps. And this is how you have to choose these blue positions correctly. With some mathematics, you can figure that out. The hardware people love this. There is just one problem. It's linear, which means if you use it as a cipher, I just write the equations of the ciphertext bits, the plaintext bits, and the key bits, and they're linear equations, and I use linear algebra, and I can break it. Okay? So what we have to do is add something nonlinear to it, and one of the ideas is to clock it irregularly, to make it sometimes move 2 times, sometimes move 0 times, sometimes move 1 times. Then you make it nonlinear, or you can add nonlinear functions, which are simple, to change the update, and this is what's being done in Bluetooth and Snow3G and Zook. So here is A51. This is a secret cipher designed for GSM, only leaked in 1995. So it was until then it was secret. It has 3 LFSRs, and they're XORed together. You can show mathematically it's the same as 1 LFSR with 64 bits. But A51 works a bit differently because you clock the registers that agree with the majority in the yellow bits. That sounds very difficult. It's very easy. If all the yellow bits are 1, you clock the 3 registers. If all 3 are 0, you clock the 3 registers. But if you have 1, 1, 0, you clock only the top ones. Okay, you always clock the ones in the majority. So these registers move irregularly. That makes it actually a lot harder to break. It's a very clever cipher. It's just that the key is too short, 64 bits. And there is some attacks. In fact, it's not very secure. But you could make a bigger cipher with the same principle with much larger registers, which actually would be quite secure and simple. But so exhaustive key search 2 to the 64, but then the police was not happy with this. The devices were too expensive. They told the operators, you should always put 10 key bits to 0. So it's only 2 to the 54. So the way to break this, what you do is you guess the content of the 2 smaller registers, and then you can also predict the clocking sequences, and then you can solve for the last register. That's a bit of mathematics, how to do this, a bit tricky. So after 10 years, people finally found good attacks. So in 3 or 4 minutes of ciphertext, you can actually find the key in 10 minutes on a PC at the time. So today, this is probably like 10 seconds. Okay? And then in 2009, people published tables, and with these tables, they did some clever pre-computation, and with these tables, you could recover the key within a few seconds. And the tables were 1 terabyte, which was a lot of data in 2009. Today, 1 terabyte is just it's a huge USB stick, that's all, right? You can just share it. These tables are available on the internet. By the way, it's still illegal to tap GSM traffic or any mobile traffic. The difficulty was still get the signal because the GSM signal is hopping around. But then finally, Noel and some others, they found an old phone where they could hack the firmware. And of course, every phone can find the signal because otherwise you couldn't talk. And so they managed to actually get the signal from this phone. And it was very interesting because this phone on eBay, the day after the announcement, became 100 times more expensive because everybody wanted this phone to be able to intercept GSM traffic. But so this was designed deliberately by governments to be very weak, but still good enough. And by the way, this cipher was only available in Europe and the US. In Asia, they got a weaker cipher called A52 that looked more complex, but actually was even easier to break. So Bluetooth looks much better. It has also 4 LFSRs. To make it nonlinear, it has here some AND operations. So, AND, but addition operations, not AND, add operations, sorry. So this is over the integers. So this is not linear. This has AND gates and XOR gates and AND gates. And so people first thought it was quite secure, 128-bit key, but then some researchers showed, in fact, that you could break it with a few million frames in a few seconds today on a machine. So E0 is badly broken. It still sits forever in all the old Bluetooth devices. The new standards have better ciphers. And then the final design I show you is a really nice design, but you should never use it. But look at it just for its beauty. It's designed by Rivest, the R in RSA, professor in MIT. And it's one of the first software ciphers. So all these ciphers were designed for hardware. This is for software. And the key, you take the key, and what you do is you produce with it a permutation of all the bytes between 0 and FF. So you take all the bytes, you write in byte 0, you write a 0, in byte 1, you write a 1, and so on, and then you permute things based on the key. So now you have a random permutation. This is how you start. Okay, you can look at the details. And now RC4 has actually 5 steps. It's the simplest cipher I've ever seen. So it has 2 pointers, I and J pointer. The I pointer just runs to the table and comes back. So I is I plus 1. The J pointer jumps by as much as I indicates. So here I indicates 0. So S0 is 205. So the J point, so I will be incremented. Sorry, then I take S, I is now here. The value in 1 is 92, so I will jump J by 92. So J now goes from 2 to 94. I will now swap the values pointed at by I and J. So it was a permutation, it's still a permutation. I will now add those 2 values, 162 and 92, and I will look at the address, which is 254, and this is my output byte. It's a very, very simple cipher. Once I explain it to you, you can remember it forever. If you leave out one step, it's ridiculously insecure. But you can't do it less. Okay? But, so it was used for notice nodes, but also was used at some stage in 2010 by Google, where you think, like, what were you thinking, or 2011? So in the 90s, it was only available with a 40-bit key in Europe, which was, of course, not enough. In fact, the best known attack to recover the key is completely impractical, 2 to the 240. So we still don't know, if you give me the key stream, how to find the key. So it's still very secure in that respect. But it turns out that it's not random. The second output byte is 0 with probability 1 over 128, which is 2 over 256, so twice as much as it should be. And so there is lots of papers written about the statistics of this thing, and the bytes are not random. And so when Google decided to use, in 2012, RC4 for browsing, people showed that if you can use a script to make the same web page encrypted many times, you can actually recover the whole web page because of its non-randomness. A very spectacular attack. I mean, we all knew that RC4 was bad. I mean, nobody thought, like, are you really going to use this for browsers? And then people showed, if you do this, look what an attack is there. The other reason why RC4 is famous is that it was the first cipher used for wireless data, for Wi-Fi. And the first Wi-Fi standard was WEP, Wired Equivalent Privacy. Since when does a wire give you privacy? Anybody believes the wire gives you privacy? I can just put a tap on it and I can read what's happening. Well, web is the same. It gives you no privacy because it uses RC4. But the problem is web needs an IV per packet. And the people not so smart who designed web put the IV also in the key input. Which means that if you analyze RC4 carefully, you look at the key processing, you learn part of the permutation from the IV, and you can choose part of it. And then, of course, it's an easy exercise, well, a few weeks of work, and then you can actually find how to recover the key. So very quickly, people produced tools, WebCrack and so on, that actually were able to recover web keys. Why? Because RC4 has no IV. Then they just put it in the key input. Now, I can recommend you to study the web protocol, because the web protocol is amazing, because all the mistakes you can make in applying cryptography badly in network security are done in one protocol. There's not a single mistake they've forgotten. Everything is wrong. The authentication is wrong, the IV is wrong, the encryption is wrong. Web is the best example of the worst possible way you can use cryptography for network security. So luckily it has been fixed now. Okay, so we worry about exhaustive key search. And there is also more clever attacks, but they will bring it a bit too far. So you can also do kind of clever techniques where you pre-compute a lot of key stream for certain memory states. And so this means that stream ciphers typically need a 256-bit memory rather than 128-bit memory. Otherwise, there is a clever attack, but I'll never ask you about this. Okay, so at least we finished stream ciphers. Next Thursday, we'll move on to block ciphers. Okay, and apologies for missing the break, but at least we stop a bit on time.